Hello, everyone. Welcome to the session. We'll just wait for one more minute and then we can get started. Okay, I think we can get started now. We have enough people on the stream. Um, okay, so this is the second day of the whole system design series. So this is what the plan we had, and we covered the day one, which was last week. I hope all of you have seen the session. So in the last session, we covered the fundamentals, which was basically we understood what is the framework to approach. Uh, Basically, what's the framework to approach any system design? What How do you basically get started with in a system design interview? How do you gather the requirements? How we understood about functional, non-functional requirements. Then once you have your requirements in place, how do you go about how do you go about estimating the capacity of the system? So that's what we covered in the first session. Even if you have not seen it, please go ahead and watch it after this session. And so this is a continuation of the series. Now today we'll learn about what happens next after you have your requirements and capacity in place. Then what should the next steps be like? So the next step is basically going about designing the high level of the system. So for designing the high level of the system, you have to understand the building blocks that come into picture for designing the system. So there can be a lot of things. There can be server, there can be first of all, there is an application. It can be a web application, it can be a client side application. There can be servers, there can be databases, there are caches. There are a lot of things that come into picture. Basically these are from like a high level scope. So we'll understand about all of those high level building blocks today. That's what's the agenda of is for the today's session. We won't be able to cover all of the high level topics because due to the time constraint, but we'll cover about most of the I'll start off with like some of the important topics, and at the end the topics that I'm not able to cover, I'll just list down a few topics and you can go and read on your own. There are a lot of resources available online that you can learn about them whenever you get time. So we'll get started. So we'll learn about like the basic, like the starting point of a high level system design. Uh, so data partitioning. This is a very primary concept. Any system design out there, even if it is a high scale, a medium scale, or a low scale, has some sort of data partitioning. So before we understand data partitioning, I want to explain uh, where it comes from. So let's take an example. Let's say if you're given a task to maintain a phone directory of everyone in your college, or if you're working in your office. So in the beginning, the phone directory can look something like, let's say you have somewhere between 100 to 1,000 people in your college, and you're maintaining a phone directory for all of these students. So this can contain, like, let's say, uh, obviously the name of the student, their contact number, their email, their address, and like basic primary details. So you start off with maintaining such a database for, let's say, a college. Now, as I mentioned, it can contain somewhere around 100 to 1,000 databases, 100 to 1,000 records. So the size of this record will be something, let's say, a few MBs to maybe a few GBs, and it can easily be put inside one database. Any database you choose out there pretty much has the scale to support this kind of database size. Now as you scale, you can understand, like, if you want to scale the system up, you want to, let's say, go one level up, you want to add more you want to scale it beyond your college. Let's say you want to also add a few different colleges in your town to the same database. Now the size of the database will exponentially increase. Now let's say in your college there were 100 students. Now you are adding 10 more colleges. The database size increased 10 times. It's 1,000 now. So now let's say we go one level up. You are not just storing the records for everyone in your town, but you're also storing, let's say, in your state or in your whole country. So the database size exponentially keeps increasing as you increase the scope of, as you increase the scale of the user base. So now when this happens, what happens is the size of the database goes beyond the capacity of any database. So what is the next step looks like is basically you have to partition the database. So to so you, if one database can't handle all of this data, you have to incorporate more than one database that can handle all of the data at one time. So that's the whole idea uh, behind data partitioning. Now we'll get into more technicalities of this databases. Let's say there are two kinds of database partitioning you can see in the diagram. One is horizontal, one is vertical. So it's pretty much, you can understand from the term itself. So horizontal would mean partitioning the database horizontally. So on the left hand side you can see you have, so basically you have an employee database where you have an ID, you have a name, age, state. So you're doing a vertical partitioning. So after vertical partitioning, we have two databases. We have two partitions, partition 1 and partition 2. So partition 1 contains ID and name, and partition 2 contains ID, age, and state. So basically, we have split the database vertically. It's pretty simple from the term itself. Now, the second one on the right is the horizontal partitioning. So here, what happens is you split up the database horizontally. So you can see in the database we have four records. In horizontal partitioning, there are, here they have talked about two kinds of partitioning. So forget about the types of partitioning for now. I'll cover it later. But what happens is we split up the database horizontally. So uh, in the first in the first record you can see there are in the first partition you can see there are two records. In the second partition again there are two records. So basically you have divided the database horizontally, and you have split up the number of rows in all these different partitions. So once you have uh, let's say in both vertical and horizontal we have two partitions here. So once you have these partitions, you can split these partitions across different databases. So this helps you scale when your database scales. This helps you basically store all of the data in split across multiple databases. So this is the whole idea behind database partitioning. Uh, we'll talk about, there are a lot of especially in the horizontal partitioning, it is also called sharding. There are multiple types in which you can horizontally divide the database. So we'll talk, and the next topic would be understanding what are the different types in which we can horizontally partition the database. So primarily these are the five techniques to shard the database. Shard, again, shard is also is another name for horizontal partitioning. So first is the range base. So if you look at the diagram on the right side, so what happens is we choose a key. So let's say it can be any primary key of the database. So here we have the ID. So what we do is we assign a range. So let's say the first partition contains any range between 1 to 25. The second partition will contain range from 26 to 50. So we have assigned a range based on the ID. So you can see once the partition happens, the first one contains any records between 1 to 25. So here we have 1 and 15. In the second one, we have partitions between 26 to 50. So we have again two records, which is 29 and 49. So this is called range-based sharding. The range again can be here since it is a integer data type. So even if it is not an integer, let's say it's a string, uh, you can have the range based on in an alphabetical order. So you can have like uh, A to G in one partition, then similarly you can split up based on the alphabetical order. So range based partitioning can happen pretty much in any type of data that you have. Second one is the hash based sharding. So here what we do is we hash the key here. So the key is hashed, and the hash value is what determines where the the particular record will go. So here, let's say we just have two shards with us. So the sharding key will be something like modular 2, which will give us value 0 and 1. So here the value that we see are 1 and 2, just for a reference. So based on the hash function, we get two values, 1 and 2, and 1 and 2 will determine which shard is also another name for partition. So which shard the data will go to. So here we can see it is pretty much split up evenly. So 1 and 29 is in shard 1, and 15 and 49 is in shard 2. So it's a hash based partitioning, and depending upon number of partitions that you have, you can modify the hash function accordingly. So let's say if you have five partitions, you can have a modular 5. So that will help you. The hash value will have like a five different values, and that will help you shard the data into all those equally among those five different shards. Now, the next one is it's called directory based sharding. So, here what happens is you can see based on the ID, there is a lookup table that has been constructed. So, the lookup table is basically helps you determine which shard a uh, particular record has been placed. So again, it can be, again there can be multiple strategies based on which this lookup table is constructed. So once we have the table, we'll just quickly look up the table and see. Let's say we are searching for 15, so we'll look up the table 15 and see that it is stored in shard number 2, and then we go to shard number 2, and then we find the rest of the records in this shard. So this is the whole idea of directory based sharding. There are also other sharding techniques. There is something called geographical sharding. So, where basically what happens if your data is spread across geographically, so you have all these different countries, continents. So, let's say if you are in India, and your database might be somewhere on, let's say if it's in a country level, it might be stored, let's say there might be a India dedicated partition which will store all the data for India. If there is like a continent level partition, it might be like your data would be stored in an Asia level partition. So if somebody is in other countries in other side of the world, somebody from US wants to access the data, so they will have a separate US based shard that will help. Basically the whole idea will be, the closer the data is to the physical location of the user, the faster the processing will be. So you can the client will connect to the closest database that exists. So that's the idea behind geographical. The last one is hybrid, which basically is a combination of all of these sharding techniques. So it can, depending, it's pretty much depends upon the use case. So you can, depending upon the use case, let's say we go with geographical sharding, and then once we are inside a particular geography, let's say you are in the India based shard, then inside the particular geographical shard you can opt for a range based shard, which will further divide the data into different shards within that geography. So it's particularly use case dependent. That's how it works. So these are like few of the common sharding techniques. There are also a lot of other techniques, but these are the primary techniques that pretty much are common and being used most of the times. Uh, let's talk about the benefits of data partitioning. So these are a few of the benefits. I already spoke about how it improves the query performance. So the closer the data, the physical data is to the request, or the client, the faster the query will perform. So it helps achieve the query performance. It also helps achieve scalability. So as and when your data keeps growing, you can't store all of it in one single database. So it helps you split up your data efficiently across multiple databases, so you can efficiently scale the data even if it is exponentially growing. We That shouldn't be a bottleneck. We can just keep adding more servers, we can just keep adding more databases, and it'll help us scale indefinitely. The next one is load balancing. It also, let's say, if you put, even if your all of your data can be accommodated in one single server, still, let's say if you have, let's say, 1,000 requests per second for the database, all of these requests is going to one single database. So the performance of the database might degrade. So if these requests are split across multiple databases, so the query can perform faster. So it helps basically balance all the load, not in just one server, but it balances the load across multiple servers. Uh, then these are like the primary benefits. There are also other benefits like data isolation. So let's say you don't you have the same data, you can also store like the copies of data at multiple locations. So what happens is, let's say if one of your server goes down, you have the copy of your data in a different server. So it helps basically have uh, like a redundant sort of approach. I think we discussed about redundancy in the last session. So it helps basically eliminate a single point of failure. Then there is parallel processing. It's similar to load balancing, where not all of your requests will just go to one server, but it is just split up across multiple servers, so you can perform more number of tasks in the same time. Then there is also data management. So we saw in the previous example, so it efficiently helps divide the database into multiple granular databases. So it basically helps you manage and structure the data more simplified and more efficient manner. So this is all about database partitioning. I think I see a few questions. I might take one. I think Suraj has asked, in scenario where data is too large, how they are managing consistency across the CDNs. Yeah, we'll talk about this. I think in the next topic, I'll cover this. So right now, so on a high level, if I would say, there can be there is a term called uh, in a distributed system, it's called heartbeat. So where what happens is basically uh, each of these, let's say there are five different variations of the server across the complete geography. So what happens is, first of all, they need to know which of these servers are there. And let's say you are in India, the India based server, you perform a write operation on that server, but this data also has to be replicated across five other different servers. So through heartbeat, what happens is, first, heartbeat is basically, you can imagine it like a human heartbeat, where each of these servers talk to each other in a, pretty much this, send requests back and forth every second or every minute depending upon your granularity. So this helps a particular server determine how many servers are live. So let's say if the India based server receives five different heartbeats, then it means it understands that there are five different servers out there. Now, once you perform a read operation on this server, so this data has to be replicated across five other servers. So once it uh, gets the idea that there are five different servers out there, it can perform a write operation on all these other servers. Now, these write operations can happen at different frequencies. So usually, the write operation is costly, where uh, you have to obtain a database log, and that's how you can perform a write operation. So usually, if depending upon the data that you're working with, if it is okay that the data is stale for, let's say, a day, you can go for a one day batch processing, where let's say every 24 hours the it's made sure the data is replicated across all these databases. If let's say you want the data, if 24 hours is it's a whole lot of time, you can't afford a 24-hour stale data, then there are companies that would go for like a 6-hour based batch processing, where the data is replicated across all of these different servers. So depending upon is it's purely depending upon the use case need, that the data would be replicated across all these different servers. And once, so that is a different part. And the reading, meanwhile, the reading can happen across any of these servers out there. So that's, I hope that answers the question. I will move to the next topic. So the next topic is databases. So again, it's very basic, one of the basic topics in systems. Uh, I'm hoping most of you would know what databases are. We are not going to talk about that. On a very high level, I will talk about the different types of databases, and we'll also cover a few examples of those databases, that some of these real world examples that are used by different companies. So the first one is the relational database. Relational database, the data is more structured. They have a predefined schema. So similar to the example that we saw previously, like there was a you're maintaining a phone directory, so you pretty much have a predefined schema. You have the ID, you have the name, you have phone number, you have address. So the data is more structured, and the schema is it's predefined, and it is also not expected to change a lot. So that's what is a relational database. And some of the examples are MySQL, Oracle, and you can read the rest of it. And then the second one is the non-relational databases. So unlike relational, the data is more unstructured. It's just distributed and have a dynamic schema. So what does that mean? So there can be instances where the structure of the data is not known beforehand. It is also expected to change a lot. So it can happen you're designing a system, you are not able to predict that what how the data is going to evolve, let's say a month later, a year later. So you start off with some sort of schema that serves as a starting point, but that at the same time you know that this schema is supposed to evolve over a period of time. In that case, it's a good idea to go for a non-relational databases. Now, in non-relational, there are primarily four types of database. So the first one is the key value store. So as the name suggests, the data is stored in key value pairs. So you have a key. It can again be any data type, integer, string, or whatever data type you choose for the key, and the value would pretty much contain all of the data. Now, the value can be structured anyway. It can even have like a JSON value. So you can have multiple nesting in the inside the database. So it can each record can pretty much go up to uh, let's say even few kilobytes or megabytes. The next one is document databases. Sorry, the key value database, I didn't talk about the examples. So there is Redis, there is Voldemort, there is Dynamo. Dynamo is by AWS. So these are the different types of key value store. The next one is the document database. So here the data is stored in documents. So instead of rows and columns, how you have the conventional rows and columns in a table, these documents are grouped together in collections. So let's say how you let's say you create a file in your laptop, you have a file name, and inside the file you put up all these different lines and paragraphs inside that particular document. So that is essentially how a databases work. And some examples are CouchDB, there's MongoDB. The next one is wide column databases. It is similar to relational, given that the data is stored in a columnar fashion, but these columns are not again not predefined like the relational, so it can keep growing. You can keep adding as many columns as possible. uh, you can also, let's say, like what it says here, we don't need to know all the columns up front, and each row doesn't have to have the same number of columns. So it is best suited for large data sets, and some of the examples are Cassandra, HBase. So, and the last one is the graph database. So, it is again, it's pretty much same as a graph. So, you have a node, you have an edge, like how a graph works. So, these databases are used to store data whose relations are best represented in a graph. Data is saved in graph data structures with nodes, properties, again the property values of that node, and then there are lines, which is also called edge, that connects these different nodes. It is also these types of database are particularly used in a lot of like social network database. Let's say if you're building Facebook, you have to have the connect. How will you determine, let's say it suggests you your mutual friends, so that is determined based on the edge. So you have a person A, you have a person B, so number of edges that are connecting these two nodes, that's what determine the number of mutual friends. So graph database are primarily used in that kind of scenarios. And some of the example of graph database are Neo4j and Infinite Graph. So these are the four primary types of NoSQL. Again, depending upon the use case, that's when we determine which database to use. So let's say once you are in an interview, and the next steps would look like, basically, once you have your requirements, you have everything in front of you, you have to determine based on the requirements that whether a relational or a non-relational database will suit your use case. And once you have that down, you can also, let's say if you decide to choose a non-relation, it'll be good if you can also break down and suggest which type of database, which type of non-relational database will be particularly helpful in that use case. And some of these examples, it's always good to remember some of these names. uh, it's not a requirement, it's just that if you have some names handy, it just helps in the interviews. uh, so the next we'll talk about basically which one, depending upon the use case, when should you go for a relational and when should you go for a non-relational. So the first one, let's say, when should we choose a relational database? So relational database, if there is a requirement where we need to ensure ACID compliance. ACID stands for, you might have heard about ACID compliance. ACID stands for atomicity, consistency, isolation, and durability. So if you have a requirement where you need to have the database ACID compliance, especially in let's say a e-commerce or a financial use case, that's where this is the prime importance. So that's when you would go for ACID compliance database. The second one is if your data is structured and it's unchanging. We spoke about this before. So before starting the uh, before even deciding the database, if you know that your database is pretty structured and it's sorry, if your database is pretty structured and it's not supposed to change a lot, then you would go for a SQL based database. The next one is, we'll see what are the reasons to choose a NoSQL database. The first one is the data has little to no structure. So it's, let's say we spoke about key value pair, where value can be anything. So value can be a JSON sort of structure. So it need not have a structured in the form of table and columns, but uh, it can be structured in, let's say, a JSON value, a JSON based structure. So in that, you don't have a predefined number of columns or a number of records that go into the database. So in that case, it's ideal that you would go for a NoSQL database. The second one is making the most of the cloud computing storage. So here, In the first session, we spoke about vertical and horizontal scaling. So it's especially if it's a non-relational database, it's way easier to scale the database horizontally. You can bring in more number of servers, and that will help scale up the database uh, to pretty much as you go. So let's say if you see that one database is not serving all of your data, you can just add another one. And when you see the two databases are not sufficient, you can just add the third one. So this is called the horizontal scaling, and the NoSQL database are supports horizontal scaling. So you can go for a NoSQL in that case, and you can also efficiently make use of the cloud-based storage, where any of these cloud servers, even GCP or AWS, helps provide those support for scaling NoSQL database. Then the last one is the rapid development, where it's extremely useful for a rapid development as it doesn't need to be prepped ahead of time. Yeah, so it's pretty much similar to what we discussed last. If your database is continuously evolving and you don't know the structure beforehand, and there can be cases where you can't predict the structure beforehand, even if you have a basic skeleton, but the data can still rapidly change. So in that case, it is best if you go with a NoSQL database. Also, at any point, you can also switch from one database to other. So there are use cases where uh, uh, companies have started off with the SQL database and then later chose to move to NoSQL. So this can happen at any time, but it also comes with an overhead of switching from one database to a different one, and then it involves all the data migration and data consistency across all these different databases. So it comes with an overhead. So we do want to minimize that. So it is always a good idea to examine which database suits our need beforehand, make that decision so that later we don't have to go with the overhead of switching the database and then doing the migration. So this is about choosing which ones between the relational and non-relational. Next, we'll talk about database indexing. I'm just looking at the chat. I don't see any more questions right now. If you have any questions, feel free to drop it in the chat. Okay, let's talk about database indexing. So, the goal of creating an index on a particular table in a database is to make it faster to search through the table and find the row or rows that we want. So it's pretty much like a pointer like structure. So what happens is there is a lookup table. So for every primary key, it can be not just primary key, but let's assume it's a primary key, and the value of that key would be a pointer to, and it'll point to that particular row in the database. So what this does is it basically helps us easily find out the particular record in the table. So it comes in handy when you want to quickly fetch that record in the database. So the indexes can be created using one or more columns of the database, providing the basis for both random lookups and efficient access of ordered records. Yeah. So you can also, there are requirements where you want to sort the particular, based on a particular key, you want to sort the database. So even in that case, you first need to index the database. Once you index the database on that particular column that you want to sort the data, it gets very fast to sort based on that particular index. So it's advisable to go for indexing when you see that if there is a use case where you see that your database performance is decreasing. So it's always a good idea to go for indexing. Also, it comes with the overhead where indexes also decreases write performance. So you let's say you have to update the database, not just update. Let's say you have to delete a record, you have to update a record, you have to alter a record. So in that case, there is an overhead because you're not just updating the database as usual, but you are also updating the index. So in that, it does play around with the performance, but I think considering the downside, it definitely has more benefits to it. So we definitely, in most of the cases, we do go for database indexing. Um, okay, so this is all about database indexing. You can see from the diagram, it's there is a key, and then there is a pointer that stores the pointer to that particular row in the table. Um, okay, let's go to the next one. Okay, this was all about databases, database partition, and indexing. Next, we'll talk about load balancing. This is also a very important topic. Uh, so I would try to explain this based on what we covered in the last session. We spoke about vertical and horizontal scaling. So let's say you have a particular server. You have one application server that basically performs all the job for you in your particular system. Now, let's say if this particular server goes down, your entire system will go down. We don't want that. So in that case, we will replicate this database, we'll replicate this server. So we can have, depending upon the requirement, we can have different replicas of this server. So this is called horizontal scaling. So here you can see like there are two web servers, there are two application servers, there are two database servers. So this is called horizontal scaling, where we have multiple instances of the server or the database. So we avoid single point of failures, and we can also improve the performance of the system. So now once we have multiple replicas of the server, we also want to efficiently determine which server we want to send the request to. So this is where the load balancing comes. So you can understand from the name itself, it balances the load. So it once a request hits, so if you see the client sends a request, it hits the load balancer. So the load balancer determines which server to send the request to. So based there are certain load balancing algorithms that determines which server the request will be redirected to. And then once it goes to that server, then you can see there's another load balancer between the web server and the application server. Then there is one more load balancer between application and the database server. So pretty much anywhere in the system, wherever you have these replicas, you can put a load balancer, and the load balancer will determine which server the request should go to. Now, there are a lot of load balancing algorithms. Let's say there is a round robin algorithm, which pretty much what it does, it just rotates the request. So let's say if you have four different servers, it'll start with first one. The first request goes to the first, the second goes to second, third goes to third, fourth goes to fourth, and the fifth one again will go to the first one. So it goes in a round robin manner. Now, the downside here is it doesn't care about the performance of these servers. So it can happen that, let's say, the second server is not performing as good as rest of the servers. So we don't want a whole lot of requests to go to that server. If the other servers can handle more requests efficiently, then we should just send those requests to other servers. So this is where the rest of the algorithm comes into picture. So let's say a least connection algorithm. So what it does is the load balancer determines which of the servers have least number of connections. And let's say a server has one connection, other has five connections. So the new request that comes in, it will send it to the one that has one connection, so that the performance is improved. Here, connections means the number of requests that that particular server is handling. So if the server is handling that, if the server that is handling the one request, if and the other one is handling five requests, so it's always better to send the new request to the one that has least number of connections. The next one is the least response time. It is similar to the previous one, where based on the number of servers that you have, the load balancer determines the number, basically the response time of all these servers. So whichever server has a faster response time, the new request will go to that server. So if it responds quickly, that means the that particular server is functioning well, and that can handle more requests. So if there is a new request coming in, it should go to the one with the least response time. The last one is the hybrid. It is again a mixture of all these depending upon the use case. Um, you try to have a combination of all of these algorithms. There are also a few other algorithms, but these are the primary algorithms that are being used on a occasional basis. Um, yeah, this is primarily about load balancing, and again, I would say this is a high level about load balancing. There are other things that also go into the picture, which we'll talk about in later sessions. There are also like lot of health checks that happen in the load balancer. So uh, we spoke about the least response time. So what happens is the load balancer itself on a continuous basis determines the response time of all these servers. So it continuously does what is called as health check. So if there are five different servers, it will pretty much every second, if not every minute, determine the health of all these five servers so that it knows well beforehand. If a server is not performing well, it will know that it should not send requests to that server. So that is the whole idea of load balancers. um, it's also very critical to any system. So I think pretty much any system that you design, there's a high chance that it will have a load balancer. Yeah, so this is all about load balancer. Let's talk about another topic. It's again, this is also pretty important topic. It's called CDN, also known as Content Delivery Network. So let's first look at the example, the diagram on the right hand side. You see that there is a world map, and then you have forget about the technical names right now. There's origin server, there's edge server. I will talk about that later. But then you have all these servers that are spread across the world, and then you have the user. So you have a user in Australia, you have a user in India, a user in Europe, you have one in America. So you have the users spread across the entire world. So you want the request for that. If the user is in India, you want the request, you can see the request for that user in India goes to the closest server. So why does it go to the closest? Because that's how you will get a faster response time. So it is always advisable that the server to be as close to the request origination. So you can see the request for the user from India goes to the closest server. So here what happens is the origin server is basically one server that is the main server where uh, basically you can also treat it as like a starting point. That is the origin server, and all these edge servers are replicas of the origin server that can be distributed all across the world. And the next question will be like, where should we place all these edge servers? So depending upon, again, the use case, depending upon the um, so if you can also talk about some of the analytics of the system. Let's say you determine that there are a lot more users from Europe than Asia, so you want the server to be as close to Europe as possible than compared to Asia. So that will help determine the position of all these servers. So these the CDN is basically for a static data. So let's say you would have used Netflix or Prime for watching videos. So these videos or images, these are called static data. So static data, whenever let's say you're watching a Netflix, the data is served to you from the closest server for you in India. So it is not, there can be the same data, the same movie can be across different servers all across the world, but that particular movie will be served to you from, not, let's say, not a Europe or a America based server. It will be served from you, that is from the server that is designated for India, so that you get a faster response time. So this is a very high level about CDN. That's how it works. And CDN is primarily, again, for just for static data. Uh, let's read about this. So, a distributed network of servers strategically located across various geographical locations to deliver web content such as images, videos, and other static assets more efficiently to users. So, yeah, the CDN is primarily for static data. So, it can be anything, images, videos, or any other form of static data. This is not for a dynamic content where the data is supposed to change frequently. So here what happens is the origin server is again the primary server, and all the edge servers, you can think of it like a cache where all the data from the origin server is replicated across all these servers, and when a user sends out a request, the server that is closest to the user will basically handle that request. So that's the whole idea for CDN. And the primary purpose of a CDN is to reduce latency and improve the overall performance of the application. And this is achieved by serving the content from the server that is nearest to the user. Okay, so that's the whole idea for CDN. And let's talk about a few benefits of the CDN. So the first one and the most important is it reduces latency. So you're serving the content from a server that is closest to the user as possible. So the load time will be pretty small and it'll provide a good user experience. Then the next one is improved performance. It is same as if you decrease the latency, you'll have a good user experience and you will have a good performance, even if when your servers are located closer to the client. What happens is you're sending out a request to the server, you will get the response quicker. You can also have it can also helps reduce the load. Let's say you have all these replicas spread across different geographical location. It also helps reduce the load on one particular server. The next one is enhanced reliability and availability. You have all these different edge servers. So in case, let's say the India server goes down, it can redirect the new request to the next nearest server. So it helps make the system more reliable. Again, scalability, obviously you are splitting up the request across multiple servers, so it definitely helps scale your system. It also helps with the security, given that your data is guarded across all these different number of servers. So you also prevent the data from more number of security threats as compared to storing the data in one particular server. So these are few benefits of CDN. So primarily all of these applications that serve static content like Netflix, Prime, all of these uses CDN. And again, CDN, where they position the CDN, it is determined based on where the maximum user base is, so that they can place the server as close to the user as possible. Yeah. So here I've listed down a few topics. These were all the topics that I was going to cover, and these are the few topics that are also important. You can read about them. These are pretty much, again, used in almost all the almost all systems. It's API gateway, it's DNS. There is CAP theorem. There is one other theorem. There is WebSockets. There is long polling, leader, and follower. So these are a few topics that you can go and read about. Again, these are also important, but the ones that I covered today are of prime importance, and you can also read about these so that uh, it can help you in understanding some of other corner cases in the systems. So this was the whole agenda for today. I think have covered most of the high level building blocks, and now we'll go into the Q&A section. Feel free to post any questions that you have from today's session, or any question in general about the high level design, and we'll talk about those. Uh, I don't. I saw one question before that I covered. Um, I don't see any more questions right now. Feel free to keep posting your questions. Also, in the next session, we'll cover about the low level design. There we'll talk about. I think that is going to be even more interesting session where we will talk about the low level concepts like UML diagrams, basically all of OOPS related concept, object oriented programming, and we'll also talk about design patterns. So that will be primarily redirected towards low level design interviews. So that is also going to be an interesting topic, which we'll talk about in the next session. Is it connected to data science also? Um, I believe data science, there are certain overlapping topics. I don't think low level system design is asked in data science interviews. Uh, Not in my understanding. I don't think it is asked. There are a lot of other topics that are asked in data science, but I think a high level must be good enough for a data science student. Okay, I don't see any more questions. I think if there are no more questions, we can end the live, and then we'll have the low level design same time next Saturday. So do attend that. And if you have not yet gone through the previous day's topics, I will advise you to go watch that after this session. It'll definitely be helpful for you to understand a framework of how to approach the system design interviews. So please do that. And thank you everyone for attending. Hope you had a good time. I hope you got to learn a lot, and we'll meet in the next session. Bye.